Hello everybody. So my name is Anna Lähde. I'm professor in aerosol technology, and today I'm going to tell you about the research carried in my research group, which focuses mainly on the development of sustainable processes and sustainable materials for several applications. And I will keep this presentation in English, since there are a large number of my colleagues, fellow researchers and friends that are actually English speaking. However, if you have any questions you would like to ask me in Finnish, you're more than welcome to do so. And before I go on with my presentation, I want to mention something about the electron microscope image I have selected on this slide. This is an image of carbon nanoflowers and graphene seeds that are from our earlier studies. And I think this shows very nicely what fascinating world of materials there are still to be discovered even today, especially when we are talking about the carbon-based materials. So here is a short history of myself. So when I look back in time, around 25 years from now, I found myself working at the VTT Technical Research Center of Finland on the topic called aerosols, and more specifically, aerosols released in a severe nuclear accidents. Back then, I actually knew very little about aerosols because I got my master's degree in chemistry from University of Jyväskylä. And basically, aerosols back then meant me something like hairspray or something similar. So last thing I was kind of thinking or imagining back then was that I would be one day standing here being a professor in aerosol technology and giving you a lecture about what extremely fascinating things the aerosols are. So shortly, the history, I got my master's degree in chemistry and PhD degree in chemistry 2008 from University of Jyväskylä. But during that time, I was actually working at VTT and also Helsinki University of Technology, or Aalto as it's called nowadays. Then when I got my PhD degree, I moved to Kuopio. I continued the research in aerosol science and material synthesis, especially about the materials related to the lithium-ion battery materials. In 2014, I got my title of docent in fine particle and aerosol chemistry. And then there is a year 2017, which was very significant to me, since I got first ASLA Fulbright CDR scholarship that enabled me to go to work in Lawrence Berkeley National Lab in Berkeley, California. And I also got my Academy of Finland Research Fellowship, which kind of led to me to this point where we are creating these new structures related to the carbon materials to different applications. In the following year, 2018, then I got the tenure track position as an associate professor, and finally last year, 23, I became a full professor. So I'm very happy to be here today and share my vision and also mission related to the sustainable processes and materials with you. So sustainability and circularity, these are the hot topics actually nowadays. Sustainable processes, materials, and applications are of course tightly connected to sustainable utilization of our natural resources. And this means that we are actually worried about the shortage of the natural resources in near future. What is the carrying capacity of the Earth with all this consumption that we are doing, how kind of the sustainable production and life cycle considerations we can make to improve the situation from now on. And also, of course, there will be a huge impact on the economy. So if you look at the right-hand side figure here, it shows you the expectations, what kind of materials we will be needing in next 25 years, and what are the applications. There are the applications, of course, mainly related to the electric vehicles, for example, renewable power, energy generation, and so on. However, it is very, very difficult to estimate the amounts or sufficiency of the resources because, in fact, we really don't know what we will be needing in 50 or 100 years from now. There is a very good example of this. Like nobody guessed in 1970s what is the position of coal and carbon materials that it has nowadays in our everyday life. In addition, today, for example, if we look at the 1980s, we didn't have the mobile phones, which are the common consumables nowadays. So we have these high-tech products currently, such as mobile phones that require substances, including lithium, indium, niobium, tantalum, that we even didn't think about that we would need back in 1980s. So this is a very, very difficult task to know what is needed in next 100 years, for example. Then the sustainability and circularity, of course, deals a lot with the considerations of the life cycle of materials and products. And this is another very important topic. For me, it was very surprising that actually 60% of the EU's waste material flows, they are so-called hidden flows, which means that there is a huge amount of raw materials that actually do not end up to a product, but become as a waste already in the very, very beginning of their life cycle. So this is some of the issues that we are trying to focus in my research. Of course, then we are dealing about the sustainable processes and productions. And I come from the natural sciences, so the technical issues are more close to my heart. But there is also one thing that should be considered, which is the socially sustainable growth. So this goes beyond, of course, to my expertise, but I want to mention this because this is a kind of a multidisciplinary research challenge and requires close collaboration between the different research fields, and that's what we are also trying to accomplish. Here is a report from the European Commission, and I selected this figure because it shows very well how the current technologies and the materials are linked together. And if you look at the sectors, you can see that there is all these fields that are now considered to be very important in the green transition. So there is a renewable energy, there is the electric transportation, also the defense and space. And the technologies that we are applying for these are including several very well-known things like batteries. We are very relying on the lithium-ion batteries at the moment to be carbon dioxide-free transportation, to enable the carbon dioxide-free transportation, for example. There are also the fuel cells, wind and solar cells. So all these technologies require a huge amount of materials that are in supply risk. And this supply risk means that they are categorized as a critical or even strategic materials. So how to deal with this kind of materials? Of course, as I mentioned already, there are a huge amount of side flows that we don't even take into use at the moment. So we are trying to, for example, in Finland, trying to collaborate with the mine industry to be able to gather those side streams. Then there is, of course, the technologies and the materials used in these technologies. So can we replace some of these materials with something else? For example, there is a natural graphite, for example. We are very dependent on the export of China. On the other hand, the synthetic graphite is made from the fossil fuels. So we are trying to find out the ways to make it more sustainable, creating a bio-based graphite. And we have actually done this already like several years, and we have very promising results on that. And then, of course, there is a future. We don't never know what new technologies we will have. And then, of course, the recycling at the end. So we should ensure that once we have made these materials, we are also able to recycle them back to use. And this involves especially the lithium-ion batteries that are the hot topic nowadays. So the research in my group is focused especially on the materials and technical solutions. So we are applying new and emerging technologies, including aerosols and thermal processes for material production. And we also try to apply the green chemistry principles on the production. And this means that we are focusing on the waste prevention. We are trying to use less hazardous chemicals. We are trying to develop methodologies or technologies that are energy efficient and can use renewable feedstocks, for example. We have developed and studied several different aerosol and thermal processes shown in here. These are actually, we also have a pilot scale facilities, so we are working very closely in the industry. So it's not only the fundamental studies that we are carrying out, but we are actually trying to make innovations that would support the industry and the green transition. Aerosol processes are very, very interesting. They can be actually considered to some extent as a green chemistry, following the green chemistry principles, because we can use, minimize, example, the use of solvents. We can change the solvents mostly to the water or other mild solvents instead of the very strong acidic solutions, for example. And this, of course, minimizes the hazardous waste coming from the reactions. And these processes are more or less one stage. So once you put the material, the precursors in, on the other end, you get the dry particles that can be directly applied to your application. So more precisely of the processes, on the bottom left-hand side, you can see the flame spray pyrolysis. We have used it in several different studies, producing a high amount of nano-sized particles, including the lithium-ion battery materials like lithium iron phosphate, which you may find in some of your batteries, for example, in the electric vehicles. We have also produced lithium titanate, which would be the wonder material. It would have a much more longer cycle life than the current batteries that we have in our mobile or other applications. Then we have also created new photocatalytic materials, and very recently we have studied also carbon dots. And this now actually links, the carbon dots as themselves have of course very wonderful properties, and they can be applied in several different places, but there is also a link in this aerosol, fundamental aerosol science, so we are better understanding what kind of properties this black carbon or soot may also have and how it impacts the environment. Then on the upper right-hand corner, there is a spray drying reactor where we have carefully been able to develop and control new type of particles. This is the picture of the nickel manganese cobalt oxide, which is also a lithium-ion battery material. And even though it looks very, very simple, sometimes it's very difficult to form these solid particles with accurate properties. So this is what we are looking for and focusing, trying to apply both the experimental and modeling parts together. And finally, on the right bottom-hand corner, we are utilizing these high-temperature processes, which are especially good for the generation of the graphene and graphitic structures. And this is actually what started in my Academy of Finland Research Fellowship project, where we studied especially this process and developed it further. One of the main applications in my research is the energy storage. This includes, of course, the current lithium-ion batteries, but also the next generation batteries like lithium sulfur, for example. And this is because you probably have heard that the lithium-ion batteries, they are not sustainable at the moment. There is the chemicals, critical minerals such as cobalt, nickel, lithium, as well as graphite, that needs to be imported, needs to be created. So for this, we have studied alternative ways to improve the sustainability of the materials. And one of the most important topics in my research group is the generation of graphene and graphitic structures that can be synthesized either from the bio-based precursors, such as barley straw, barley husk, or industrial side streams as lignin, which is abundantly available, and there is currently no good use for the lignin, for example. So this would alleviate the problem and challenges related to the synthetic graphite that is produced from the fossil-based precursors, or the natural graphite that is mainly imported from China. And as I mentioned, we are not only limiting our studies to the current energy storage systems, but we are also trying to make them better and improve and improve the current technologies. So as you can see from the left-hand side graph here, lithium-sulfur batteries are the next upcoming battery technology. And it can offer much higher specific energy density compared to our current lithium-ion batteries. And of course, in reality, this would mean that our electric vehicle would go actually significantly longer distance than it's currently doing. It has been estimated that it can go over 2,000 kilometers with one charge. So this would be a huge thing. Also, lithium-sulfur batteries are much lighter, and they can be applied in a solid-state batteries. So there is also hope for their aviation. So this could mean that in future we would hopefully have also the carbon dioxide-free aviation. So shortly about the high-temperature thermal graphitization of the bio-based carbon that we have been carried out and studied very long time. So we can take any lignocellulosic or agricultural side crops, for example, as shown in here. We went to the fields and collected barley straw. And then we can do the chemical activation using conventional pyrolysis or hydrothermal methods, or go directly to the high temperature treatment up to 2600 degrees Celsius. With the catalytic processes, we can control the formation of the graphene sheets or the graphitic layers, as shown on the right-hand picture. And this is very interesting because actually biomass, the production is about 146 billion tons in a year, which carbon accounts 20 billion tons. So this precursor is actually very abundant and readily available, especially in Finland. The lignin is readily available at the moment and relatively cheap to be used. So why graphene? Just very shortly to show you a quick overview, because graphene, which is a one monolayer sheet of carbon atoms, has very, very fascinating properties. It's very strong material. It's almost transparent. It has a high electric and thermal conductivity. However, nowadays the single layer graphene is very, very difficult to obtain, and we have learned that we don't need to actually have the single layer graphene in our applications. We can also use the bio-based multi-layer graphene in our battery materials, for example. And then there is also one more thing about the carbon precursors, and that's of course the carbon dioxide. And currently we are also working the carbon capture and utilization, and we have developed these new materials, including, for example, CIF8, CIF8, which is a geolytic type imidazolate compound with very specific selectivity to carbon dioxide with a very high surface area. And together with other professors at the UEF and also the international collaboration, we are currently converting and studying the conversion of carbon dioxide to precursors for different olefins or directly to carbon and graphitic structures. So this is the end of my presentation. The motivation throughout my research career has been the excitement of finding something new that would make the world a better place to live for all of us. And I would be very happy to answer any questions you may have, either in English or in Finnish. Thank you.